Hey everyone, today we're going to be working through a conceptual incline problem. We're going to be drawing force diagrams, analyzing the net force, and working with pure variables. Let's look at the problem. We are told a small block of mass, m, is released from rest at the top of a frictionless incline of angle theta and length L. We are also given our kinematics formulas, so we don't need to memorize these. Let's draw out our situation and a force diagram. We have our incline, which is length L. It is at an angle theta, and we have our block at the top of it. The only forces acting on this block are a force of gravity, pointing straight down, and our normal force, which is perpendicular to the incline. However, to make our forces useful, we all want them either perpendicular to the incline or along the incline. So we're going to have to split up our force of gravity into its components. One component is going to be down the incline, and one component is going to be perpendicular to the incline, opposing the normal force. Let's figure out how we're going to calculate the values of that. For this, we're going to have to draw a couple right triangles. Since this is a right triangle, we know that this angle right here is going to be 90 minus theta, just because all three of those angles need to add up to 180. The second triangle we're going to draw is like this. Another right triangle. However, we know that these two angles are 90 degrees. So 90 minus theta plus this angle in red right here have to equal to 90. So the red angle is going to be theta itself. So I'm going to redraw this with this new information so we can figure out how to split our force gravity into each of its components. Now, with our updated information, let's figure out the magnitude of this force, the force that's pointing opposite of the force normal, and the force that is going down the incline. Since this force opposing the normal force is adjacent to the theta, it's going to be equal to force of gravity times cosine of theta. And since the force going down the incline, which can be represented by this force right here, I'll draw it in red, is opposite to the theta in our right triangle, then that will be Fg sine theta. So that is going to be our force right here. I'm going to redraw this once again now with our finalized force diagram. This is now our finalized force diagram. Let's go into our questions. Part A asks us to derive an expression for the acceleration of the block down the incline in terms of g and theta. Real quickly, I'm just going to redraw our situation. We have our incline with theta, we have our force normal, we have our Fg cosine theta, and we have our Fg sine theta. To solve this question, we're going to have to ask ourselves, what is our net force acting on the block? Now, the block is only sliding down the incline. It is only moving in the direction of Fg sine theta. It does not move in the direction of the force normal or the Fg cosine theta. Thus, we know that force normal equals Fg cosine theta, so they cancel each other out. Thus, our only net force is going to be equal to Fg sine theta, which is down the incline. Now, to actually calculate the value of Fg sine theta, we just have to remember that the force of gravity is equal to mg. So, our net force equals mg sine theta, and net force also equals mass times acceleration. Let me rewrite this equation down here. To solve for our acceleration, we're just going to need to divide both sides by m, and we get that acceleration equals g times the sine of theta. Let's look at part B. Find the speed v for velocity of the block when it reaches the bottom of the incline in terms of g, l, and theta. So we can treat this like 1D kinematics because our acceleration is in the exact direction of our movement, just down the incline. Since our block was released from rest, we know our initial velocity equals 0 meters per second. We calculated that our acceleration was equal to g times sine theta. And our delta x will be positive L. This means that down the incline is our positive direction. Let's figure out the equation that we're going to use based on what we know so that we can solve for velocity. The equation we're going to use is v squared equals v initial squared plus 2 times acceleration times delta x. Let's substitute what we know. So v squared equals 0 plus 2 times g times sine theta times L. If we take the square root of both sides, we can solve for velocity and get that velocity equals 2 times g times the sine of theta times L. Part C. Determine how long it takes the block to reach the bottom, t for time, in terms of length, g, and theta. Based on this question, we know a couple things. Again, we know that our delta x equals L. Our acceleration is g sine theta. Our initial velocity equals 0. And our final velocity equals the square root of 2 times g times sine theta times L. To solve for t, there are two different equations we can use. Let's go through both of them. The first one is delta x equals v initial times t plus 1/2 at squared. Let's substitute what we know. So delta x is L, which equals 0 times t plus 1/2 times g times the sine of theta times t squared. L simply equals 1/2 times g times the sine of theta times t squared. And we're going to multiply 2 over g times sine theta on both sides. We're going to get that t squared equals 2 times L over g times sine theta. Take the square root, and we get that t equals the square root of 2 times L times g times sine theta. So that's one way to arrive at this answer. The other way would be to use the equation v equals v initial plus a times t. We can substitute what we know and see that the square root of 2 times g times sine theta times L equals 0 plus g times sine theta times t. We can ignore the 0 plus and just see that we can divide both sides by g times sine theta and get that t equals the square root of 2 times g times sine theta times L all over g times sine theta. However, we can simplify this. So to get the denominator into the square root, we're simply going to have to square it. So t equals the square root of 2 times g times sine theta times L all over g times sine theta squared. Now, one of the g times sine thetas on the bottom is going to cancel with the g times sine theta on the top. So we're still going to have 1 g times sine theta on the bottom. So we will get that it's the square root of 2 times L over g times sine theta. Same answer as the other equation. Part D is going to be our challenge problem. It asks us, if another incline has the same height h but is twice as long, what happens to the time to reach the bottom? Express the ratio t2 over t1, with t2 being the time it takes for the object to reach the bottom when the incline is twice as long, in terms of geometry or constants. Let's look back at our equation for time. It is t equals the square root of 2 times L over g times the sine of theta. Now, what's important to solve this is to remember what sine of theta can represent. So if we look back at our incline, this is theta, and it can form a right triangle with our incline, where the hypotenuse is our L and our opposite side is our h. Sine of theta equals h over L. So let's go ahead and replace that in our equation and get that t equals the square root of 2 times L over g times h over L. We can simplify this, moving the L to the top to get that it's 2L squared over g times h. And let's remove the L from the square root because it's now squared, getting L times the square root of of 2 over g times h. We can now see the relationship between time and length. Let me rewrite it so it's a little bit clearer. If we keep the height the same, everything else in this equation is a constant. But if we double our L, it's simply going to double our time. The way I like to demonstrate that relationship is to make everything 1. So L equals 1, G equals 1, and H equals 1. I know that's not the case, but it'll show our relationship between the two variables a little bit easier. So when we get that t equals 1 times the square root of 2 over 1 times 1, or just the square root of 2. Now, we want to double our length, but keep everything else the same. So now L equals 2, G equals 1, H also still equals 1, and now our t is equal to 2 times the square root of 2 over 1 times 1, or is equal to 2 times the square root of 2. So it has doubled when our length doubled. Thus, our ratio t2 over t1, t2 was when the length was doubled, equals 2. Thank you for listening.